So we've learned what an equilibrium is. We've learned what the equilibrium constant is and what its significance is. Now we're going to learn how to actually calculate equilibrium constants and use them. Equilibrium constants do depend on temperature. So you will often see that a temperature is given. You can kind of just ignore that. It's given because they are temperature dependent, but the temperature does not come into the calculation in any way. Concentrations are needed. The concentrations are always going to be in moles per liter. That is a unit that we'll come back to in chapter 12. But for now, you know what moles are and you know what liters are, so you can be okay with that. When we do these constant expressions, there would be units on them, but just as a convention, we drop the units. So an equilibrium constant does not have units. The concentrations in an equilibrium situation will not always be the same, but the equilibrium constant at a particular temperature will be the same. So it's describing the position of the equilibrium, not the actual concentrations. So let's look at this reaction. We've looked at it before. Where's my pointer? There's my pointer. Hydrogen plus iodine going to hydrogen iodide. Suppose a mixture of these is allowed to come to equilibrium at 445 degrees Celsius. Well, there's a number, but we can ignore that. We don't really need that. The measured equilibrium concentrations are given here. What is the value of the equilibrium constant? What we need to do is write the equilibrium constant expression and then put the given numbers into it. So KEQ is the equilibrium constant, and that equals the concentrations of the products over the concentrations of the reactants, and they'll be raised to a power equal to their coefficient. So the product is HI. So in the numerator, we have the concentration of HI, and in the equation up here, this has a 2 in front of it. So that means I square this. This is coming back to you. Then in the denominator, I have the concentrations of the reactants, H2 and I2. Those have coefficients of 1, and so they're going to have exponents of 1. Well, I don't need to write those. That's the equilibrium constant expression. They give me concentrations for these, and so I need to just put them in. We're not going to try to trick you with concentrations and make you convert those. These should always be capital M. Capital M means moles per liter. That's all it means. And we can basically ignore that because the equilibrium constant is not going to have any units at all. So I'm going to take the concentration of HI, which is 0.78, and that has to be squared. And that's divided by the concentration of H, which is 0.11, times the concentration of I2, which is 0.11. So 0.78 squared divided by 0.11 divided by 0.11, I get 50. 0.28. Each of the values here had 2 significant figures, so we should round this to 2 significant figures. 50 point, that's acceptable, but 5.0 times 10 to the 1 is better. That's the equilibrium constant for this particular equation. There's not going to be units. All of the equilibrium expressions are a little bit different. In this one, the units actually would cancel out because you've got capital M squared divided by capital M times capital M. They actually cancel out in this example. Other examples, they do not. And instead of figuring them out and writing them down when they're really not necessary, we just decided to ignore them. So we always do concentrations in moles per liter, and then we ignore units on the actual constant. Any questions? This, the publisher didn't provide me with a digital copy of this, so I used my cell phone and took a picture of your book. I think this table is helpful. So we just calculated this example right here. These are the equilibrium concentrations of the 3 species in this reaction, and we plug those into this equilibrium expression and we get 50. That's if we started with half a mole of hydrogen and half a mole of iodine and no hydrogen iodide. If we started with none of the reactants and half a mole of product, we'd end up with these concentrations. How do we know that those are the concentrations? They have to be measured. So if I plug these numbers in, I get 50. If we start with half a mole of each and let it go to equilibrium, measure the concentrations, plug those numbers in, I get 50. If I start with 1 mole of hydrogen, half a mole of iodine, no product, let it go to equilibrium, plug the numbers in, I get 50. The equilibrium constant is constant. It doesn't change at a particular temperature. Okay? So it doesn't matter what concentrations you started with, the equilibrium constant will be the same. Any questions? Let's do another one. Consider this reaction. We have a mixture of these 3 substances, carbon monoxide, hydrogen, and methanol, and it comes to equilibrium at 225 degrees Celsius. The measured concentrations are given here. What's the value of the equilibrium constant at this temperature? Same idea as the last problem. First, we write the equilibrium constant expression, and then we put in the numbers. So KEQ is the concentration of the product, CH3OH. There's no coefficient there, so there's no exponent, divided by the concentration of carbon monoxide, which also has no coefficient, and then hydrogen, that has a coefficient of 2, and so this becomes squared. Any questions about that? Now we just put the numbers in. The concentration of methanol is 0.151. The concentration of carbon monoxide, 0.489. The concentration of hydrogen is 0.146. And then that needs to be squared. Now it's a matter of communicating with your calculator. If you need an intervention, just come up to my office hours and I'll straighten your calculator out for you. So all of these concentrations have 3 significant figures, so then we'll give our constant to 3 significant figures. 14.5. Any questions? Well, so that's nice. We can calculate an equilibrium constant. Why would we want it? We can use the equilibrium constant to help us predict the concentrations at equilibrium, and that can be very useful. So if we look at this example here, COF2 is in equilibrium with CO2 and CF4. The equilibrium constant at 1,000 degrees Celsius is 2.00. So they're telling us what the equilibrium concentration of the COF2 is and the CF4, and they're asking us to find the concentration of CO2. So what we have to do is we write the equilibrium constant expression and then solve it for CO2, plug the numbers in, and we can calculate the concentration. So KEQ equals the products, CO2, times CF4, no coefficients, no exponents, divided by the reactants, COF2, and that is raised to the second power because there's a 2 here. We need to solve this expression for CO2. There's a fraction. I recommend cross-multiplying to get rid of the fraction first and then isolating the CO2. So cross-multiplying will give me KEQ times COF2 squared, and that will equal CO2 times CF4. I want CO2 by itself. I need to divide by the thing that's with it over there. Because that divided by itself is equal to 1. It goes away. If I do that on one side of the equal sign, I have to do it on the other or it won't be equal anymore. So then I divide over here by CF4. So it's kind of messy, so it's nice to just rewrite it. CO2 equals KEQ COF2 squared divided by CF4. The brackets just mean the concentration of what's inside in moles per liter. So I know that KEQ for this reaction is 2.00. And the concentration of COF2 is 0.255. And that's squared. And then I'm going to divide by the concentration of CF4, 0.118. 2 times 0.255 squared divided by 0.118. How many significant figures should this have? 3. So this one has 3, 3, and 3, so our answer should have 3. So I'm getting 1.10. This is a concentration, not an equilibrium constant. It does need a unit. What are the units that we're using for concentrations? Moles per liter. So moles per liter, or 1.10 capital M. Don't worry too much about the capital M business. I'll explain that in the next chapter. Any questions? Mm-hmm.
The COF 0.255, you squared it because of the subscript 2 or the 2 outside of the bracket?
I squared it because of this 2. In this equation, you take the concentration raised to the power of the coefficient. So because this has a coefficient of 2, I square the concentration. Has nothing to do with this 2.
Oh, so the 2 outside the bracket is the coefficient.
This 2 is from here. Yep. These have understood 1s, and these guys have understood 1s as exponents. You only write an exponent there if the coefficient is something other than 1. Any other questions? Let's do another one. Iodine decomposes at high temperature to form iodine atoms. Here's the equation. Here's the equilibrium constant at 120 degrees Celsius. In an equilibrium mixture, the concentration, oh, there's a typo, of I2. Let's, magic, I2 is 0.10 molar. What is the equilibrium concentration of I? Well, we need the equilibrium expression, and then we need to solve for the concentration of I. So we look at this balanced chemical equation, and we say, well, KEQ is the product, which is just I. It has a coefficient of 2 in front of it, so then I square it, divided by the reactant concentration, if there was a number there, it would be 1, right? This would be a 1, and this would be a 1. The chemists don't like to write the number 1, so we don't, because it doesn't matter. Okay, I know I2 is 0.1. I know KEQ. I'm looking for I. I need to rearrange this so that I get I by itself. So if I cross multiply to get rid of the pesky fraction, I get KEQ times I2 is equal to the concentration of I squared. Well, I don't want I squared. I want just I. How do I get rid of the square? Square root. So if I take the square root of this and the square root of the other side, it's still equal. And the square root of I squared is I. So the concentration of I is equal to the square root of KEQ times the concentration of I2. So that's the square root of 0.011 times 0.10. Two sig figs, so this comes out to 0.033. And the unit is going to be capital M, because in these sorts of problems, the unit is always capital M for concentrations. Any questions? Your faces are just so interesting.